Welcome to a demo video for dilemmas, De Morgan's theorem, and solutions to the sampled problems at the end of the PowerPoint slides. This is Philosophy 1290 Critical Thinking with Phil Veltos. The first problem in the dilemma response strategy was this dilemma. We captured it as reopen or suppress. If we reopen, then they'll have a high infection rate. If we suppress, then many businesses will be bankrupt. So therefore, we have to choose between a high infection rate or many bankruptcies. And we formalize that. We get premise 1, a disjunctive premise, R or S. R then H, S then B, therefore H or B. So we'll start with the satisfying ourselves that this is in fact a valid argument. And so we have R, S, H, and B. And then we have first premise R or S, second premise R then H, third premise S then B, conclusion H or B. We have 1, 2, 3, 4 variables, and so we need 2, 4, 8, 16 rows on this truth table. This is quite an undertaking we're about to embark on here. True, false, that's 4, true, false, 8, true, false, 12, 16. Then we do double true, double false, double true, double false, double true, double false, double true, double false. And then 4 trues, 4 falses. Remember my comments in the videos about how the practicality of truth tables evaporates fairly quickly as your arguments get more complex. I think, I shouldn't even be talking at the same time here. Those are all trues for 8, and then 8 falses. The next step in our process is to come over to the conclusion and find the cases where the conclusion is false. So that is going to be, we have H or B, so only the rows where both H and B are false. In a case where both each, remember this is an OR, as long as at least one of the disjuncts is true, the result is true. So we're going to have true, 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 and we're going to have a lot of trues in a row here. So I've lost 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. And then here we have true, true. Oh, I'm sorry, it should be true, 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 false. Every fourth one is false. True, 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 false. True, 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 false. True, 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 false. So we have the 4th, the 8th, the 12th, and the 16th rows are the ones that are interesting. So working backwards now, and it helps, especially when you're doing this freestyle without lined paper, to make sure you're not getting your rows crossed up. So I'm filling in all these blanks until I find at least one premise. for every false conclusion. So S then B. S is true, B is false, so that's false, and as a result that row checks out. On the next row that matters, row 8, S then B is true. So we got to keep looking. R then H, true then false, that's hit the target, don't get the prize, false. So that checks out. Row 12, S then B, true then false, is false. That checks out. On row 16, S then B, false then false is true. H, false then, or R then H, false then false is true. And then R or S, false or false is false. And so there we have it. The dilemma is in fact a valid argument. So remember, that was this dilemma, which is the classical form of the dilemma, right? Often called in logic textbooks the constructive dilemma. There are other forms, typically with negatives, that would make it something else than a constructive dilemma. Next, we wanted to, I feel like I've stolen a paper here. Next, we wanted to do the slightly more complex form, although you'll see, in fact, that this is a nice, simple version of the dilemma, right? So there's only two variables, but it has that same basic structural form: disjunctive, two conditionals, and then a disjunctive conclusion. What makes this form interesting is that the disjunction is, the first one is P or not P, which we will see is a tautology, and then this. So we wanted to, remember, we wanted to prove a couple things here. We wanted to prove, is that equivalent to R? And is this a tautology? So let's start with the easy questions first. Is P or not P a tautology? So we'll work this out in excruciating detail. So under the P we have true and false. Under the not P we would reverse this. So if P is true, not P is false. If P is false, not P is true. We bring those two results together. True or false. Remember, the or is true as long as at least one half is true, so true. And in the second row, this one is true, so true. So that's a statement that's true. I mean, there's only two possibilities, and in both cases, this statement is true. So that's a tautology. The next thing we wanted to determine is R or R logically equivalent to R? So R or R is true on the first row, and since neither R is true on the second row, that would be false. On this side of the equivalent, we would just repeat those values just to be clear where everything's coming from. And then is true the same as true? Yes. Is false the same as false? Yes. And so we have a tautology there as well. Okay, so that settles those two issues. With that, let's assess the entire argument. So for P and R, so starting with the conclusion, we're going to have true, 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 this is R or R, true, false, false. So we're interested in rows 2 and 4. On row 2, we have not P then R, so P is true, so not P is false, and R is false, so the result there is true. Here we have, on this row, we're looking for P then R, hit the target, didn't get the prize, false, so that checks out. On this row, P is false, therefore not P is true, and R is false, and so true then false is false, so that checks out. So that argument is also valid. Remember, this one here was true all the way down, right? That's a tautology. So if we'd not find the right falses here, we would not have found them here. That premise was going to be no help to us at all. The next thing we wanted to satisfy ourselves the truth of was De Morgan's theorem. And we're going to do both versions just because we need to practice with these truth tables. So we'll do this version and then we'll do this version. Notice that they have a similarity structure, except basically this is moving the negative from outside the bracket to in using the and versus the negative outside the bracket with the or. Okay, so this is going to be a bunch of practice here. We have negatives, we've got ands and ors, we've got all sorts of things to get good with here. It's a 4-line table because it has two logical variables. So true, false, double true, double false. So under this little bunch of squiggles here, we want to make sure we do their squiggles in the right order. Now, inside the brackets comes first. So where's P and Q? So that's going to be true, false, false, false. And then we do the negative. So now we're going to negate this. So if it's true, then it would be false. And if it's false, then it would be true. And now, once we've gone outside the brackets, we should stroke those out so we don't confuse ourselves later. We have this value we're going to bring over here, but we need to do this one first. So now that we're over inside these brackets, the negatives come first and then the bracket. So not P would be false, false, true, true. Not Q would be false, true, false, true. And then we do the or, so false or false is false. False or true is true. True or false is true. True or true is true. And now we ask ourselves, using the equivalence operator, is false the same as false? Yes. Is true the same as true? Yes. Is true the same as true? Yes. Is true the same as true? Yes. And so this is a statement that's true under all possible circumstances. That's called a tautology. And so when we see something like this later in induction, you'll say, yes, I know how to go from ands to ors because I saw it in De Morgan's theorem. And just because we want to get even better at this, we're going to do the other version. So again, for P and Q, so now we'll work inside the brackets and then out on both sides. So here we do the or first. This is pretty simple. P or Q is going to be true, 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 false. And then we negate that. So we get false, 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 true. And we're going to bring that over to here. On this side of the ledger, we're going to have to do the negatives first, then the and inside the brackets. So P is true, so not P is false. That repeats, and then P is false, not P is true, and that repeats. Over here, it's going to be the opposite value. So when Q is true, not Q is false. Q is false, not Q is true, and that repeats. And then we do the and. So false and false. Remember, ands are true when both halves are true, and false the rest of the time. So we're going to have false, 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 true. And we bring that result over here. False is now, and then it's equivalence. The triple bar is equivalence, which is same as. We put true whenever these two are the same, and false if they're not the same. On all four rows, they are the same. So let's get into some problems. So in better times, we would just put these up on the projector and then solve them on the whiteboard. But we'll do the best we can here. And remember that when people speak in ordinary language, they don't say, I am about to make a statement or I am about to make an argument. They're just going to tell you what they say. And you, the critical thinker, have to decide, what am I looking for here? Is this a statement? Is this an argument? So looking at this very first one. Neither the fox nor the lynx can catch the hare if the hare is alert and quick. Is there anything there that sounds like a argument? Is there a thus? Is there a therefore? Is there any premise indicating words? I don't think so. So I think this is just a statement. So then we just have to put it in form, which means it's going to be all in one big long thing. So, and then we might say, okay, let's call F is fox catch hare, and we could have L be the lynx can catch the hare, and then we could have H be the hare is alert and quick. And then we have, okay, so now we've got all our atomic statements. And then we have to say what's the logical operators here. We've got neither nor, which we think of as a or, right? We got lots of words that do this logic work. And then we've got an if. And remember the rule, if the antecedent is always what comes after the if. So the fact that the if is in the middle of the sentence here tells me that what the form of this is going to be is H, then not now it's neither nor, and F is, so it's not the fox catching the hare, and it's not the lynx catching the hare. What do we do about our brackets here? If the hare is alert and quick, then the fox can't catch the hare, or the lynx can't catch the hare. Does that seem right? Or should it be if the fox is alert and the hare is alert and quick, then it's not true that either the fox or the lynx will catch the hare. I like that one as being accurate to the original, and this one, well, this one, quite frankly, demorgans would tell us that would work if we put an and there. So, but this is probably more fully captures the language of the or in the original. You can either stay at the hotel and watch TV, or you can go to the museum and spend time there. Now, the way our language works is not easy, let's face it. But one of the things we want to watch for is we often precede an or with an either or an if with a then if we want to sort of help us understand which is the major logical operator, right? So in a way, we're doing a little bit of bracketing here. So I think that this is the big logical operator. It's, you know, if we're thinking about it, that's the final one, the one that you would do last in a truth table. And these ands, if we even decide to keep them, would be secondary logical operators. But let me take a shot at translating that in the simplest way possible. Simplicity is a virtue here. So how about if we have HB watch TV at hotel and MB spend time at the museum. Have I done any discredit to either of those statements? I don't think so. And then I get a real nice H or M. It wouldn't be wrong to do something like, you know, let HB stay at hotel and TV watch TV, and MB go to a museum, and SB spend time, and then we would have H and T, or M and S, but that's way less elegant and a whole lot more work for what amounts to the same thing. Both of those, in my opinion, are correct, but this is preferred. If I read the newspaper in the kitchen, my glasses would be on the kitchen table. But, and remember those buts are like ands, I did not read the newspaper in the kitchen, so my glasses are not on the kitchen table. That word so probably tells us we're looking at an argument. And so we got to find our atomic statements. If I read the newspaper in the kitchen, so let's call that R. I read the newspaper in the kitchen. My glasses would be on the kitchen table. But I did not read the newspaper in the kitchen. Okay, so that's R again. So my glasses are not on the kitchen table. That's this one again, but notice that we just have to capture those two negatives there. So now our form is, if I read the newspaper at the kitchen table, then my glasses would be there. I did not read the newspaper at the kitchen table, so my glasses are not there. If you're asked to assess that, you say, okay, we could do a few things here. One of the things we could do, and this is the reason why I showed you those argument forms, is we could say, you know what, this argument looks pretty familiar. Does it remind you of any of the classic argument forms? Here we have the antecedent and the consequent, And then the second premise says that the antecedent is false. Isn't that denying the antecedent? Now, is that a good thing or a bad thing? And you might flip back to your textbook. You might go to your memory and say, aha, that is the fallacy of denying the antecedent. And therefore, I recognize it as invalid. We could also maybe come up with a counterexample. If I was really smart, I'd be teaching philosophy. If I was really smart, I could come up with a counterexample. I can't come up with a if I'm not really smart, therefore I cannot come up with a counterexample. There you go. And if neither of those methods are jumping to your the front of your mind, well then we can do a truth table. So for R and G, okay, so just double check that we've got the entire argument here. Looks good. So then this is going to be a nice simple 4-line table. Not G is going to be this in reverse, so it's going to be false, true, false, true. Lines 1 and 3 are the interesting ones. On line 1, R is true, so not R is false. That line checks out. On line 3, R is false, so not R is true. And on that line, R then G, false then true is true. And that shows invalid. So notice we got 3 possible systems here. We can recognize the form. We could come up with a counterexample. We can do the truth table. Any method is fine by me. Notice that the truth table method is easily the go-to method if you want to be really, really sure, but also really doesn't cut it when it comes to assessing arguments in real time in the public square, so to speak. No one's going to be impressed when you work this out on a napkin at a restaurant. If we could ever go to restaurants, then please don't do this, because you'll convince everyone who already has taken critical thinking, but they came up with a counterexample in their own head already. Meanwhile, everyone else who doesn't know what these squiggles mean is none the wiser. So, recognizing by form, pretty good. Also, not as convincing for people who don't know. But what I find is by saying, "Oh yeah, that's a certain fallacy," then with a little bit of practice, coming up with the counterexample not too hard. Okay, moving right along. This one, and I'm not going to do it again, but we did do this one during the Q&A on Monday. So and I have the videos for that up in the propositional logic section of UM Learn. Okay, so that is one we don't have to do tonight. And I think at least one of the classes I did this one as well. And it's a little tedious, so you can check in the Zooms for this one as well. But let's do this one. Something is an elementary particle only, ooh, there's that only word. We hates that word. Only if it has no parts. Nothing which has no parts can disintegrate. An object that cannot be destroyed must continue to exist. So an elementary particle cannot cease to exist. Okay, so I see a so that probably tells me this is the conclusion. Now we have this only. Something is an elementary particle only. So that, let's call that E, or elementary particle. Only if it has no parts. Now what do we do with that only if? Is this, if it has no parts, then it's an elementary particle? Or if it is an elementary particle, then it has no parts? What's going on with this here? And remember the rule for onlys, stop, drop, and think, which usually means try it both ways. So we could have, let's call that has no parts, and we've got to be careful. There's that no there that we have to be careful about. I'm not sure that no here is a negative so much as it is a number. What do you think about that? If it has no parts, I think it means 0 parts. Nothing which has 0 parts can disintegrate. So I don't think we want to treat that as a negative. We've already got a nothing here. Okay, so then we have something is an elementary particle, then it has no parts. Let's call that N. Or should it be, if it has no parts, then it's an elementary particle? Only if. What do we think? Which one of these is the right one? If it's elementary, then it has no parts. No parts. Right? Sounds like what this is. Look, there's only one way to be an elementary particle, right? If it's elementary, then it has no parts, or if it has no parts, then it's elementary. This one allows things that are elementary that have more than one part. This one doesn't. Think about the only is trying to exclude something here. What is it trying to exclude? It's trying to exclude that there are elementary particles that have more than one part. So I like the first one. If it's elementary, then it has no parts. Okay, so rocking along, nothing which has no parts can disintegrate. So that's if it has no parts, then it cannot disintegrate. So that would be N, then not D. An object that cannot be destroyed must continue to exist. Now, do we think that destroyed and disintegrate here mean the same thing? I sure hope so. Otherwise, this argument is going to get really complex unnecessarily soon. So, an object that cannot disintegrate must continue to exist. Yeah, that works, right? If you want to be sure if it can work to treat them as the same, then you take one word and substitute in the second place and see if it still makes sense. And nothing which has no parts can be destroyed. Yeah, okay, so it's there, it's going to work. So an object that cannot be destroyed or cannot disintegrate must continue to exist. We probably want C for continue to exist. So if it cannot be destroyed, then it must continue to exist. So an elementary particle, E, something is an elementary particle, then it cannot cease to exist, or it would continue, right? Cannot cease to exist, and we've got continue to exist. How do we make all that work? And I would say that negative has to disappear, and we get a C. Now that's a whole lot of work, but what we've got this one over here, E then N, N then not D then C, therefore E then C. So we got E, N, D, and C, 4 variables. I usually put them down in the order in which they appear in the argument. This order is random. Okay, what do we think? Anyone got any, while I'm writing down all these trues and falses, anyone got an opinion? 1, 4, 4, 8, 12, 16. About whether this is going to be a good argument or not. I would say talk amongst yourselves, but you can't. Maybe you are. Maybe you're texting each other as I do this. I support that. Had lots of complaints about Tiger not appearing in the last lecture video. Poor Tiger got caught in a sunbeam and just could not wake up. She just laid there all day. Okay, that was a pile of work. And now we do E then C. True then true is true. True then false is false. True then true is true. True then false is false. True then true is true. True then false is false. True then true is true. True then false is false. And all the rest of these, where the antecedent is true, the result will be true. So it's true all the way down. So these we're done with. Everyone see that? I'm looking at all of these falses here and saying every time a conditional has a false antecedent, the result is true. So since these are false all the way down, these will be true all the way down. So finding these false conclusions here. On row 2, not D, then C. D is true, so not D will be false, and so that result is true. N, then D. True, then true is true. E, then N. True, then true is true. Oh, sorry, I messed up. I'm sorry. This has got a not in here. Let's try that again. Do I have the wrong value? N, then D. Yes, that would be false. My mistake. Notice that I made a rookie mistake. I did not properly copy out my problem from the initial statement. And so I just about made a fool's errand there. Fortunately, caught it before we went too far down the track. Normally I make these mistakes in a live class and I get all the keeners screaming at me from the third row, and that keeps everyone awake. It's tremendous fun. Okay, on the fourth row, D is false, so not D would be true. And C is false, so that would be true. Oh, sorry. That would be true, then false is false. And so that row checks out. On row 6, D, not D is false. So that's going to be true. N, then not D, false. So the antecedent is false. You pretty much default to true there. And then on this row, E, then N. True, then false is false. Row 8, the last one that matters. D is false, so not D is true. C is false. So true, then false is false. So that's a valid argument. Notice with the shortcut method how much of this table we do not complete. Now in your textbook it does what they call an indirect table, which basically means that you try to work out which rows matter and skip all the rest. But and in a way we kind of did that. We said, hey, anything where E is false, that's not going to matter, right? But I find it way more reliable to work that out on paper than it is to do it in your head. Quite frankly, by the time you can do truth tables in your head, you're a graduate of this class. And so you'll get there, but let's do what we can tonight. I think that's been plenty. I'll stop here, and there are some more I'll pick up in a second video.